Well, what a professional setup you have. So I, in Heidelberg, actually host also a Kubernetes meetup, and we're a much smaller crowd, and we're closely knit together. And hopefully, when you look at each other, you hopefully are not sitting next to people you all know, right? Because the meetups are actually to get you engaged in asking the right questions, okay? So when I was asked to give a talk about Kubernetes, I wondered, well, who's going to show up? Are there people who already know about Kubernetes, or is it more, do I need to introduce to the topic? And as I've seen when George asked the question, maybe 10%, is that right, said that they have been already working with Kubernetes. So I think the topic I chose, oops, now it's working. A novel architectural perspective is exactly this, the topic which you would need for the rest of the 90% who's now getting into the topic. And what I did is I put together a couple of slides, and then I'll do some practical examples. And the slides basically also convey the path of how I and the cloud native teams around in SAP started convincing other business units and others at SAP to go this path. Because it's quite difficult to convince people who already are knowledgeable and have already a productive and commercially successful product in place, to convince them why do we need to switch, right? So I hope that is the right topic. So indeed, the first thing you need to understand is actually as fundamental is what is the container. And you've seen in the introductory video statements, there was always a lot of talk about containers, but let's go a little bit deeper down and understand what is the container and why do we think that in, let's say in 5 years or 10 years, something new will not happen, but that this is a fundamental technology which is there to stay, right? So in order to understand this, I always say our software materializes in operating system processes. Obviously, there are probably some of you who do firmware, software and firmware and so on, who don't have an operating system. This talk is not for you. The containers are for those who need an operating system to materialize their software. So let's take a look at the process itself. So what does a process need? The process needs obviously a CPU, no program counter, and a little bit of memory. But then the question is, how do we start this process? So in the past, you would have taken a compiler, you would compile your executable, or if it's a Java-based program, you need a Java executable and you have some modules. If it's a modular program language, you have some libraries, and you would use some kind of installation tool like yum, apt-get, install, and so on. And you would install these executables and libraries and whatever you need into the root environment of your operating system, into the root file system, or C drive, if you like, right? So the first thing what a container does is to say, or the innovation is around saying, well, why don't we give this process its own environment? That means when this process calls a function, list me all the files in my file system, it doesn't see the root environment, it only sees its own environment. It's specifically done for this process, and it contains only the libraries and the files and whatnot which this process needs. And we'll continue a little bit further. We'll actually virtualize all kinds of tables the kernel hosts for this process. So if this process asks, what's my host name? What's my network IP address, right? It doesn't get the host name and IP address of the underlying operating system, but it gets its own virtually displayed, right? So, and this goes on. There are more tables like that, the process table and so on. Everything gets virtualized. So Now you wonder, well, how do I configure this all? Where do I get secrets? There's some more environments which you need. And so the idea around the container is that configuration, secrets, and even if this process needs to save state, the storage, access to storage, all of these things are externalized from the container and are injected just before you start the container, right? So that, in essence, is the container. So the container has a boundary around it, so you can control how much CPU, how much memory is consumed. And if you look very closely to this, because this is, let's see, because the process now calls the kernel, you can actually, at this boundary level, inspect exactly what the process is actually calling, which system calls the process is actually doing. So if you notice that the process only calls, let's say, functions which are here on the left-hand side, then you can create a so-called security profile, because if during runtime you see that the process all of a sudden calls something on the right-hand side, something is wrong, right? So that is basically the notion of when you hear containers are secure by default, this is what is meant by that. You can do security profiles. And last not least, there's a difference between virtualization and containers, in the sense that the process here in the container has access to everything the operating system has to offer. You don't need enlightened drivers and virtualized drivers. So that means if you have some new hardware, like a GPU, you only need the Linux driver to run on the operating system, and you have direct access to it, right? That's a big benefit. You don't need to wait until enlightened drivers are available. So let's remember, everything in our domain is software. If the toaster talks to the fridge, or if you want to talk to your blinds, put the shades down, everything is software. And this container, or the process in the container, is the basic building block for it. There's nothing you cannot build with containers. That's number one, right? There's nothing to say that, oh, containers are too small, my big process, my big stuff doesn't work in it. No, everything runs like that, can be made to run like that. So indeed, I'm not going to go into the detail here. A container is just a process bound by Linux primitives. And if you want to learn more, the slides will be made available. Let me see, I've created a self-learning. Oh, can't. 1 second to move it over. Under this link, there's a Container 101 link, and I've been told people have used it and have learned around the details of containers. It just walks you through an hour's worth of time, right? Of your time, and then you should be knowledgeable. Okay, so let's continue. What does this bring me? So we have now established that it's an ideal runtime, but it's actually also an ideal packaging vehicle for processes. So you can set up a container registry and take that environment with the library, the executables, and package that up. It's a zip file. And now if you have a host, you just need to download that piece of container, or that zip file, and you set up the Linux boundaries, the primitives, and inject the configuration and secrets, and attach a storage volume, and you can start your process, right? So there are a number of advantages which are associated to that. I'll only focus on the last 3 maybe. So first of all, the process is completely isolated. It doesn't bring qualities, or isolation qualities with it, such as hypervisor isolation. They're much stronger. But this is, for most application purposes, this is good enough, right? The bigger advantages are around it's 100% reproducible. If that process is started, you know exactly that the environment you have started it with is what you have decided on. If you've got 10,000 hosts, right, and you want to start a process, you have all these runbook automation and patch management things. There's always one host which didn't get the latest patch, and you're in trouble, right? This stuff is 100% reproducible. Either it works or it doesn't. And last not least, because there's no hypervisor in between, um, it's as fast as spawning a process. And this is a make or break for technologies such as serverless, functions as a service, right? So you can't, yeah. Anyhow, so let's now focus a little bit on some of the principles which come associated with the container. And this is hard to get for many of us who have been doing things the old way. So first of all, I talked about the runtime confinement already, right? So you see that container, you can confine how much CPU it's using, how much memory, and there are other control groups available for how much I/O and so on. You can even freeze that container, right? So that's pretty clear. Next, though, is you have higher primitives available with respect to lifecycle observability, right? So a process, you only had the system 5 handles. Yeah, you get that for the container as well, but you can also add specifics. You can add, for example, an endpoint to for an external monitoring system to scrape metrics, right? And we also talked about it a little bit, but the idea of a container is that the image itself is immutable. So you can take this container and run it the same way in development, test, and production, and so on. This has a lot to do with the patch management, which I told you about. Image immutability and reproducibility helps you to get the same behavior in different environments. And last not least, around self-containment and disposability, you can see here we have externalized state, config, and secrets, right? But the build time is something where you put in the image immutability, and you can choose at runtime how the process in that container manifests with which environment and so on. And because you have this externalized, you have externalized basically the specifics, what you can do is you can stop a container, change the image from version 1 to version 1.1 and so on, and you can basically do updates, patching, and so on. This is called disposability, more or less. So, and last not least, again, once you have these building blocks, you can establish higher level of designs. So a container within the Kubernetes world is not run individually, but it's run as a pod. A pod is basically the context to run multiple container images within the same control group and same isolation boundary box. So that means you can actually separate different concerns. So container 1 here takes care of one thing, and container 2 takes care of something else, but they do it in a collaborative manner. They talk to each other. And so you all of a sudden see design patterns evolve, such as the sidecar pattern, right? So the main controller container here could be a web, Apache web service, and the sidecar pattern could be something which fetches the data from somewhere outside and puts it on a storage which is accessible for both. Or there's an adapter pattern where an adapter talks via the local connection, or again via shared storage, to the main container. And this is being used, for example, by Istio, by service mesh, right? That means in the adapter pattern is such that the pod, you only say, I want to run my main container, but the framework actually injects an adapter which then does the communication for you to the outside world. It is used, for example, in Istio with the Envoy proxy in such a way that you, as in your program, you do not need to take care about TLS, about SSL, handshakes, and so on. Everything you communicate is in a transparent way, but the adapter, the Envoy proxy, does all the SSL handshaking and so on, and also does the retries. If you focus into this topic more, you'll see how beautiful that is. And last but not least, there's also an ambassador pattern. I'll skip that for now. So taking all of this together, you can say that there is cloud native architecture is introducing a fundamental architectural shift. And let me explain that by these pictures here. So we are used to work with systems, with machines, right? So when we look at infrastructure as a service, that was already a big innovation. But what did we do? We abstracted the hardware, and we got basically the system as a virtual machine, as a service. The operating system itself was delivered to you as a service, but you would have to think about, how do I install my application on top? And you would do this imperatively. That means you would design your landscape. Say you need 5 VMs, you need 1 database machine, maybe 1 middleware machine, and 4 application servers. You would design it quite explicitly. So if, of course, some advantages are already there. You can with infrastructure as a code and other means, you can automate these things. So if the 5 application servers were not enough, you could automate it externally in such a way that if the workload increases, you add another machine. That's what abstracting the hardware already brings to you. But with the rise of containers, and Docker must be credited for that to make it ubiquitously available, and with orchestration schedulers such as Kubernetes, I think we can all agree that Kubernetes has won the scheduler war, right? And with design patterns using pods, we are now moving into a declarative world. So first of all, what you see here is I've taken the application design and taken it apart into so-called microservices, right? So each of these individual pod boxes there basically is a microservice, the front end connecting to the application business logic, back end connecting to the database. There might be messaging and other things involved here, but these are now individual containers or pods. And what you do is you consume the infrastructure now in a declarative manner. That means you attach auto-scaling requirements directly to the individual component. That means if the front end is now reaching a certain workload level, it automatically duplicates itself, auto-scaling, right? If the database, now that's a little bit more complex, if the database is a distributed database, the more data goes in there, the more queries it gets, it can automatically expand, right? And last not least, this is the orchestrator and the scheduler of Kubernetes. You are also running on a pile of hardware, obviously, but you're thinking about it completely different. So essentially, containers and Kubernetes make you redesign your application from being machine-centric to being application-centric, okay? So all right, so how does Kubernetes actually do that? And we'll hear a little bit more, I think, from Nikita later. We essentially establish controllers and control loops which go from an imperative design to a declarative design by measuring the system. And I've kind of depicted it here. It's an infinite for loop, which always measures what is the current state and compares that to the declarative desired state. And if it sees any differences, it makes the according changes, right? So that's one of the fundamentals of Kubernetes itself. So let's go ahead and do a practical example. So let me explain that here quickly. You can take a look at this, the code itself. So what I did is I took a Golang program, a web front end more or less, and I containerized it. This Golang program exposes an HTTP endpoint, and there are a couple of applications which take you through individual features of Kubernetes. We will not focus on all of them, we'll just focus on one. And so, yeah, I will do the following first so that we get going. I will start it, and then I'll explain you because it takes like 2-3 minutes. So indeed, in my case, oh, you can't see it. 1 second. So in my case, my application, my is built upon a couple of microservices, and you can see here. Let's see. I'll talk like this. So I have a couple of declarative YAML files, declarative states. I won't go into the detail. So I will start my front end. I will start my back end. In this case, it's a MongoDB. I will order a persistent volume, a storage piece. And I have some configuration and secrets and so on, which will not be the focus for today's demo. So once I start all of this, and I just do it with one small command, basically apply that directory, and all of these things go in. The system now starts to establish the declarative, the desired state. This will take like a couple of seconds, so let's go back to my presentation, and let me explain you what is actually happening. So indeed, I have started 2 containers with my front-end application called introspec, and I injected the configuration and secret to connect to the MongoDB, which is also containerized. It's also a container. And the MongoDB, I also gave it a configuration, a secret, and I attached also a storage volume, right? So now, how do I, as a end user with my laptop, how do I get access to this thing? And that will be the part of the second demo. So the first thing I can do is, I can say, I have a service object. Again, something, a Kubernetes primitive, which says that the service is handled. If you look at, oops, not visible. There. If you look at this thing here, you can say that this service itself has a name, but it selects, it forwards port 80 to target port 8080 to all of the containers which have a label app equals to introspect. And that's exactly what I did over here. The app is equal to introspect. So that's one way of doing it. But because it's an HTTP service, I can actually use another Kubernetes primitive called ingress, which forwards HTTP, HTTPS requests directly internally to my front end. And the nice thing you will see here is that I don't need to deal with security certificates and SSL things. This is all done by another controller. So let's go ahead and show how it looks like. So indeed, in the meantime, let me actually connect to my my Kubernetes cluster. So I obviously have used our Gardener project tool. So as you can see, oh, I have to log in back. So here's a list in Project Core. There are a couple of test clusters, and this is mine. So you can see that this cluster has been auto-created on AWS, and it already created a domain name for me, which I'll be reusing. And let me log into this one. So let's take a look at what happened. This is the Kubernetes dashboard you'll be also getting to work with. It's an open source dashboard. And you can see that in my case, there's one MongoDB and 2 front ends which have been created for me. So if I now take a look at the services, this is the first example I did. There's this introspect service, which has an internal IP address of the cluster, but I'd like to get access to it from outside. It's an internal IP address, this 100.65 and so on, is not reachable from outside. So how do I do that? So obviously, this cluster is hosted on Amazon. Amazon offers load balancer services for them, for routing traffic from the outside to the inside. So let's do that. So let's expose our internal service via an L4 TCP load balancer. So what I'm doing here is I'm editing the resource object of the service directly in the Kubernetes system, right? This reflects the actual up-to-date state of that object. And here you can see the type is a cluster IP. That means it's an internal IP address. So what I can do now is I can say I would like to order a load balancer. And that's it. So now what's happening is, let me refresh this page. All of a sudden, a cloud controller integrated with AWS saw the change, saw that the desired state has changed, and now is creating an AWS load balancer for me. So this load balancer will take about 2 minutes to start, so because there's a DNS name and so on, which needs to be ordered, so it's not immediately available. So after 2 minutes, we'll revisit this page. So that's one way how to expose your service, your internal front end, to the outside world. But we can do much better. As mentioned earlier, we have here the object ingress. So what I'm doing is I'm basically saying my host name. So part of this domain name has already been given to me by the Gartner system. But you can see I'm just taking a wildcard entry called intro. And I'm also not only doing that, I'm not only forwarding requests to this domain name to a backend called introspect, right? But I'm also ordering an SSL TLS. And I'm doing that by using annotations which another controller works upon. So there's a let's encrypt automated way of receiving SSL certificates. So when I apply this ingress desired state or specification document, 2 controllers will go ahead and do its work. One is the Nginx internal load balancer, this is the internal load balancer, and the let's encrypt to fetch the TLS for me. So let's do that. And immediately, because here the load balancer has already been set up, I have access to my application, and notice the SSL handshake is secure. It's a valid certificate, right? So this is quite helpful, but sometimes you don't want to use the domain names which have been given to you by say, the service provider, right? Like this funny, let's actually, in the meantime, take a look if that, oh, there's this one here. So this is also working. You can see here, this is not secure. This is HTTP forwarded, right? So by the way, during meetups, this is not a conference. Mistakes can happen, yeah? So people should be free, but no mistake happened. Okay, so you can see that if in the Gartner case, I already had a nice domain name, but if I would be using AWS, I don't like this funny UID host name and so on. So obviously, I did something in the background. I have my own domain name called Act Virtual. So I had already set a DNS entry, and what I did earlier with the ingress object, I did another one pointing to my domain name, introspect@actvirtual.com. Much nicer, and you can see it's also the SSL certificate is auto-loaded for me. I didn't have to do anything, right? Okay, so let's actually see if it works. So my guest book program here, Masu was here. Let's submit it. Seems to work. So my front end is working with my back end. Okay, good. So that was this demo here. So let's go ahead and do something else. So typically, I have a version 1.0 running, and I would like to update my, my installation, my microservice installation. So what I will do next is I will, first of all, react to higher workload. I will scale my front ends. Then I will actually update version 1.0 to version 2.0, and then I see a mistake and I do undo a rollback. I do a rollback. So let's do that. Again, let's see, how do I get... Seems I have to get out of presentation mode. Okay. So for this, I'm using a nice little application which I found, which actually demonstrates you what's happening live in the system. So you can see here, I actually have my Kubernetes cluster is only on one node, and it takes too long, but if I would scale my application to so many containers that one node wouldn't be sufficient, Gartner would kick in and actually auto-scale the cluster as well, but I won't be doing that. You can see my internal service object called introspect with the internal IP. It's pointing to, at the moment, 2 instances, container instances or pod instances, and you can see here, replica is equal to 2. So what I'm going to do now is I'm going to scale the replicas to 3 deployments. And as you see, with yellow here, a 3rd pod was created. And now I'm going to do a rolling update to the version 2.0. And the way I do it is I actually edit the live state of the Kubernetes primitive or object called deployment. And I'll go and find my image. So here you can see image, the container image called 1124 introspect, version 1.0, and I'm going to change it to version 2.0. I'm going to save it, and let's take a look at how this unfolds. So you can see in yellow, 2 new versions were being downloaded and started, and one version 1.0 is being killed. Now the 3rd version 2.0 is started, and you see the 1.0 is gone. That's it. So actually, let's see if my application still works. Indeed, it's version 2.0. But I found this is a mistake. The color, I don't like it at all. So let's take a look at what actually happened in the rollout history. And you can see revision 1 was when I scaled it to 3, and revision 2 was when I edited it manually. I did some manual changes to version 2.0, and I want to go back. So I just say undo deployment. So, I have to go back to. So everything is done back. So you can see the version 2.0 goes back to version 1.0. Right? So again, you can see in the version history that I've now a revision number 3, which is back to what was done before. All right. So at this point, you would say, okay, I have I've seen some practical examples. This is all okay. Mm, in the past, I've learned to apply my application on bare metal systems. Now I've learned on virtual machines, and now cloud native is coming along. It's just a new piece of underlay. Um, I don't have to actually, um, yeah, this is it. This technology is coming and going. I just have to keep keep myself up to date. So here's an argument which I find compelling why Kubernetes is more than just an infrastructural tool. So in my opinion, what's happening is you've seen these stacks many times. There's hardware underneath, and you get infrastructure as a service, and on top, you put platform as a service, and in the end, you get software as a service. And typically, you will find like technologies such as Cloud Foundry, they're positioning themselves as platform as a service tools. And if you're new to Kubernetes, you will be thinking, if you work with it, even the practical example showed it a little bit, you would think Kubernetes is just in the infrastructure area, right? So I think, and you'll be working with volumes, containers, storage options, services, networking. This is all very close to infrastructure. And this is how you will be first experiencing Kubernetes. And in my opinion, this is actually totally the wrong way to look at it. And I would argue that you should look at Kubernetes in a totally different way, because with that Kubernetes has an extensibility across all the layers. You can actually, of course, order storage, compute, and networks using Kubernetes. That's what you've seen. And you can, using these low-level primitives, you can create backing services. But, and you might have heard about Knative and other means, even Cloud Foundry is being containerized. You can create platform as a services on Kubernetes. And if you look at functions as a service or web IDEs, which run on Kubernetes also, you could think of it as, well, that's, as a developer, web IDE is a software as a service. Functions as a service is also a little bit like software as a service, right? So, and I was having a hard time to explain this to others. So now let me take you and explain you my path of how I viewed it, and it's a little bit philosophical, right? So to understand this, you have to know the term emergence. And you've often heard the term, the whole is greater than the sum of its parts. It's attributed to Aristoteles. I think in English he's called Aristotle. But this is the way I learned to write his name. And he says, that's his thing, the whole is greater than the sum of its parts. And that's a quality you would like to have in a platform, right? So that when you put things together, they form something higher. And emergence is the definition is an emergent property is a property which a complex system has, but the individual members do not. And when you put them together, they form a higher order of behavior as a collective. And my example here, and I'll be reusing it, is a triangle, right? So the triangle has two sides, back and front. It's got three edges, and it obviously has orientation, right? So far with me? Very easy. Okay. So, and now I'm going to take these triangles and put them together into a Möbius strip, right? So all of a sudden, I get an emergent property, because now this Möbius strip only has one side, and if you follow the edge, that's the trick about it, you only have one edge, and the orientation is gone, right? Unless you crunch the Möbius strip and do something with it, yeah? Okay, follow me so far? Okay. So the Kubernetes system has exactly this property, the emergent property. Why? Because if you go to the API server, you are allowed to install triangle objects. You're basically connecting with triangular objects, which can be connected to each other. And how is that? So first of all, it has a uniform API signature, right? So within Kubernetes, you can obviously plug in anything you want, but if you want to talk to Kubernetes, you have to talk to it using a uniform API signature, which is extensible. And on the other side, all the basic rule sets like authorizations, role-based access controls can be made to control how you look at these triangles and what type of triangles can be put in there. So the Kubernetes system is extensible in that way that you can create your own triangle object, and you can actually install your own controller. And that means you can actually paste in a declarative, self-reflective specification document where you can put in your objective. Your objective can be very big. It has a version 1.0. You can actually define everything on your own, right? And then your controller has to do whatever is necessary to do the needful and activate that or control that subject of your desire, right? This could be internally to the Kubernetes cluster, like spinning up another container or pod, but it could be also controlling the blinds in my house, right? Or in your house, yeah? So, and not only that, so the controller, instead of doing everything on his own, can rely on desired specification state documents which other controllers are doing. So we saw this, this example with the SSL certificate, right? So this controller can spin out other spec documents which go back to the Kubernetes API. So you can actually build upon each other. And that's how you build a platform, right? And this is a quality you should seek in other systems. So if you look at and try to essentially evaluate the quality of a platform, it's the recursiveness which you should be looking at. So learn how to do Kubernetes, make it recursive, right? And then you use other things which are already there. I like this quite, this is a nice example. So I'm running out of time. My next example would be a useless machine, and it depends on how much time we have. I would need 2-3 more minutes. Is that okay? All right. So let's take a look at this in action. So anybody knows what a useless machine is? Have to explain it? Okay, so there's the on and off button here. So, and if you click the on button, if you click the button to on, that wooden piece there goes up, and a small hand comes out and pushes it back to off. Huh? You haven't seen it? Okay. Okay. So let's do that. So indeed, I'm creating basically a so-called CRD. And as mentioned, Nikita has some much more detail because she's actually worked on the community project on establishing a CRD. So what you see here is, so I'm using the Kubernetes extension API, and I'm establishing a new API, essentially. And in my case, the group is called introspect@virtual.com, and the kind is useless. And the spec which I allow is a required, a desired state, which means on or off, right? I'm defining a new specification document, and it should be Boolean. Yeah. Okay, so I've actually done this already, so let's take a look. This is the API. This is a direct connection to the API server, and you can see the API server hosts a lot of APIs, and one of them, don't know if I can find it, there it is, APIs introspect@virtual.com version 1.0. It's already there. So And my introspect program has a so-called operator example. So let's connect with this. This is a front-end UI. And let's create a useless machine. So you can see the API version, introspect actvirtual.com version 1. The kind is useless, and I'm creating useless machine version 1 with a desired state of 1 to be on. So let's apply that. The cluster is hosted in Europe, so there's a little bit of latency here. There is my machine, useless machine. So if I click it off, it goes back on, right? And this is not fake. So this is actually the moment I switch it off, the Kubernetes state document is switched to off. That means the state is changed, and the controller then sees it and then turns it back on again, and the UI reflects the actual state. And I had to build in wait times because the system obviously is much, much faster. So let's do another one, another machine which has a desired state off. There's some latency. Let me just refresh. There's my second machine, and it goes the reverse way. And I will prove to you that this is actually true, that I'm not faking anything. I'm going to edit the live state of the specification of the resource object in the backend of the Kubernetes system. So I'm going to say the desired state should be off. And watch this useless machine here. So, and this is my quota era demonstrandum, QED. So thank you all for your patience.